Okay. So I would like to start from the last expression which you have seen yesterday, namely the one of the amplitude at 4 point written in spin-helicity variables. So I'm just gonna repeat this since we'll use this as a starting point for simplifying this further and possibly inferring some of the properties which then we will follow at higher points. So there's two pieces in these amplitudes again, and the way I wrote the color structure, I mean the dependence on the gauge theory indices, is through the structural constants. With a particular way of writing the normalization. And we see here that the two terms are obtained by permutation from each other, and they yes, present some analogies. Very good. So this is the stopping point from yesterday. What I would like to do today is look a little bit more in detail, at least starting from looking a little bit more in detail on how we write the color information about this. And first, I would like to consider a different normalization for the structural constant. So far, I have used the structural constant normalization, which you would see in a quantum field theory textbook, or at least most quantum field theory textbooks. But let me just note that different normalization it is employed for reasons which will be clear in a second. So instead, we would like to change the normalization of the f so that FAB, this -2 factor is absorbed. And we're gonna just call the new f's with an f tilde. Okay, this is however not the only change in normalizations, because also we want now to consider, just for simplicity, a matrix group. So we will just consider generators of the group which are matrices, and they are normalized as, so that their trace is equal to the delta, Kronecker delta, without a factor of 1/2. I would say most quantum field theory textbook you will find a factor of 1/2 here. Not all of them, however, this normalization is very widespread, the one I'm using as well, particularly among the amplitude community. So just note this, that this may not be your favorite representation matrices. They may differ by a factor of square root of 2. So using these matrices, you get that the commutation relation is as follows. There's a factor of square root of 2 in here. But also this can be rewritten as f tilde. So this is why the f tilde is good with this normalization. TC with factor 1. Okay, very good. And using this, we can, of course, this is equivalent to writing together with use of this relation, the f tilde ABCs as the trace of the commutator TA TB with the matrix TC. Okay. The reason for the choice of this normalization being that this comes without any multiplicative factors, together with the fact that, and now we will, maybe I'll write it in this corner, we will specialize to a CUN. And employ the completeness relation, which is the following. So we have two matrices, and I'll try to indicate with a capital letter the adjoint index, contraction, so sum implied among the adjoint index here, and we have the indices, the representation indices, fundamental, anti-fundamental, I, J, K, L, there's a completeness relation, which is delta I, L, delta J, K, and then minus 1 over n being the number of colors, and the job of this term, of course, is to make this manifestly traceless. Concretely, with a choice of SUN, I'm going to have that my representation matrices are traceless Hermitian generators. Okay. So using this, then we can rewrite the color part of the amplitude in a way that instead of having our structure constant, it has traces of representation matrices. And this will be useful for us because those traces carry with them an information really about an ordering, so that we have a natural ordering of the external lines. Let me just show perhaps with a certain degree of detail. You decide whether it's too much detail and I should skip it, or it is too little detail, but let me just show for once how this would look like. So here we would have TA, I mean, we just write this structure constant as traces. Here we would have TC, TD commutator into with TE, and then we just use the completeness relation. So what we will get is commutator TATB. This with indices JI. Here we would have the completeness relation inserted, IL delta JK. There is, of course, the trace term. And here there is the other commutator, which I write as a commutator with indices explicitly displayed L and K. Okay, so just by using this, we write this as an overall trace of the two commutators paired. Okay, where we see that the term with 1 over n vanishes due to a combination of cyclicity of the trace and the fact that this will become a trace of the commutator TAB, so the two terms cancel each other. Okay, so we write down explicitly here this with all the color structure TAB. So there is one in which you have all the orders, the usual order. Then there is trace of TA, TB, TD, TC. Then there is minus the trace of TB. Here, using cyclicity of the trace, I can always write this in a way that the first element is the A, or the one corresponding to the first leg. So in this particular case, I would have minus A, TC, TD, and then using cyclicity, I put B here, plus trace of TA, TD, TC, TB. Okay. So we are using, in fact, the fact that the trace is cyclic, and using this particular expansion for the amplitude, then a general amplitude, and let me express this at n points, can be cast in the following form. So we are having that our amplitude would be a summation over pieces, each multiplying one of these traces. And using cyclicity of the trace, we always put leg external state number 1 in position 1. And here we are going to go having TA1, and then there will be TA of sigma one where the summation here is over permutations of, I indicate as a sigma permutation of the n minus 1 elements to n. So this would be the first element, and then you would go all the way to a sigma n. Okay, so I call these objects, which would be I guess, a important object in writing an amplitude in a way that the color information all goes into the trace. These are called partial amplitudes. And I will try to be notationally clear on the difference. Since I indicate both of them with A, I will try to indicate each time which one is a partial amplitude and which one is a color-dressed amplitude, let's say, or just an amplitude. Okay, so this can be used to rewrite the expression which we previously obtained. And this will allow us to obtain a little bit more clarity about what are these two pieces in which the amplitudes was written. So far, any questions about these steps? I think you can see an echo also of the way string amplitudes were written in the other lecture in here. And just using this expression, say repeat the same step which we have done for the other contraction of structure constants, you would have that the amplitude, the total amplitude following this organization is written more explicitly in the following form. So now we have a 1, there's an I, again a kinematical part. Here I repeat the one, I don't simplify the bracket in numerator and denominator for reasons that will be clear in a second. And here we have a bunch of traces. So this is the traces which were written before. TA trace of TA, TB, TT, TC minus the trace for TA, TC, TD, TB plus trace. And this is really just keeping track of the various terms. So the complexity here is just keeping track of the permutations. And then there is another term, 1, 2 to the 4th, and here there's a differential, we say, ordering in the numerator. So 1, 3, 3, 2, 2, 4, 4, 1, factor of I, and here we have different orderings. TA, TC, this being obtained by, you know, which permutation you got from here to here, so you apply the same principle is in here, TB, TD, and then there is minus the trace of TA, TC, TD, TB, minus the trace of TA, TB, TD, TC, last element, plus the trace of TA, TD, TB, and then TC. Very good. Okay. And now we want to organize the terms. So in this particular example that we have made, what are our partial amplitudes? The partial amplitudes can be read off this equation. Just you look for the corresponding trace over there, and these are the partial amplitudes which you're getting. And we note in particular that the partial amplitude of 1, 2, 3, 4 in this particular case is just identified as one of the two pieces of the amplitude before. So there's a factor of I, 1, 2, 2, 3, 3, 4, 4, 1. Then there will be a second partial amplitude here, A4 of 1, 3, 2, 4. And then we go look for the 1, 3, 2, 4. Where do we see 1, 3, 2, 4 is exactly this. And note, for example, that the same trace structure we don't see in the other one, right? Unless I have made a mistake, you are not going to find the same trace structure. So this is the other term, which we find 1, 2 to the fourth. And now we see, and we start understanding how this denominator is written, because we see that the ordering, right, this particular structure in the denominator has a certain ordering, I mean, and this is the same ordering which you see now associated to the partial amplitude through the traces. So 1, 3, 3, 2, 2, 4, and then cyclically 4, 1. Cyclic symmetry, which you see here, corresponds to the symmetry of the trace. There is another element in here, which actually is quite interesting as an aside comment. Well, let's consider another amplitude here. We have A4, and I can consider 1, 2, 4, 3. What is this? Well, this is going to have two terms, right? 1, 2, 4, 3. So we see here there is this term, 1, 2, 4, 3 is the ordering, but we see that the same term occurs also in this particular case, in both cases with a minus sign. Okay? So by writing this explicitly, we have a 1, 2 to the fourth power, it's always there. We have something in common. Here we write all the denominators, so we have a 1, 2, 2, 3, but there's also 1, 3, 2, 4, 3, 4, and then there's a 4, 1. So, and then we collect now together the two terms, and these two terms are a 1, 3, 2, 4, minus 1, 2, 3, 4, which are the two terms. And now we understand that this is a Schouten identity. So by using of the Schouten identity, this term can be rewritten as 1, 4, 2, 3. How do we see this? Well, you just consider the permutation. 3, 2, 4. There's a minus sign, so this is 2, 4. You can see this as a plus 2, 4, 3. And then this would be the result of the Schouten identity. So once this is written completely out, after using this identity, we see that the expression is analogous to the one which we saw before. So namely, we have here a 1, 2, 2, 4, now corresponding to this order, and then there is a 4, 3, and then there is a 3, 1. Okay, very good. So in this simple example, leads us to essentially a question. What are the properties that these partial amplitudes obey? Questions so far about this? Okay, let me know if I'm putting too many details. Or here I was really in doubt. Can I just say this is the result and that you need to use a Schouten identity, or do I have to work it out? And I opted for the latter one, but please let me know if I am giving you too many details. Okay. So we have the example here on this side. I keep the example, and I would like to now discuss the properties of partial amplitudes. So a first property will be the fact that they, of course, enjoy some cyclic symmetry. So the first would be cyclic symmetry in the sense that if we are having an here for 1, 2, n, or any permutation thereof is just equal to the same, but just with 2 and 1. This is in a sense something which is almost part of the definition with the traces that comes directly from the trace property. A property that you can observe but is slightly less trivial is the reflection. So the reflection is actually, if you like, a consequence of the fact that whenever you're going to find a term in here, as you can see in this simple example, you're also going to find up to a sign the term with the reverse order. The term with the reverse order being sometimes obtained after using cyclic permutation of the trace, in a sense that here we're having that these terms and these terms have the reverse order. Of course, to see it explicitly, I just need to put the TA at last, but it is there. Actually, if you do this carefully, at higher point, you would find that there is a sign coming from the multiplicity. And this is the n with the reverse order, n to 1. So this is another, and I would say this property, it emerges by construction. I mean, if you are assuming constructions in which these traces are coming from a structure constants and you do this at whichever multiplicity you want, you'll end up observing this. But there are also some properties which are a little bit less obvious. And one of these is the photon decoupling identity. Stop me if I'm going too fast. So the photon decoupling, this is a series of identities which has I will explain where this name is coming from. But essentially, we see that we consider a UN gauge group instead of an SUN gauge group. So difference being an extra U1 or a photon, if you like. Now, if we construct this, you see that none of the gluons is charged under the photons. In fact, this is a very, like, it's kind of a boring theory to consider, if you like, at least at 3 level. So the photon needs to decouple. But how do you incorporate, I mean, this property is manifest at the level of the presentation of the amplitude in terms of the Fs. But how would you incorporate this? Well, the photon would have now one of these matrices proportional to the identity. So what does this concretely mean? That because of this property, we are having, by replacing one of the matrices, say leg 2 with the identity, we would have that you would need to get a 0, but that the 0 comes as a combination of partial amplitudes, which are actually obtained by keeping the fixed order for the other legs and having 2 in different orders. So let me just write this, and hopefully will be a little bit more obvious. So you have an AN here. This is the 2 being in this position. 1 is always fixed. You have 3 and then 2 all the way to n. Then you have AN 1, 3, 4, 2 the way to n, and you keep adding with 2 being inserted in different positions until 2 is inserted in after n, and this needs to be equal to 0. This is, I mean, at least to my mind, this is already a non-trivial identity. And there is a learning lesson in here. The fact that these partial amplitudes These are, of course, as I have defined, this is n minus 1 factorial. I mean, depends on a permutation which fix due to cyclicity of the race the trace, the first the first leg. So there's n minus 1 factorial independent of those. They are not actually independent. And this produces, raises the question of whether additional identities can be obtained. Yes. Okay, so the meaning of the photon decoupling identities is that you know that if you consider a slightly different theory in which you don't have SUN as the gauge group, but you have UN, at 3 level, you're going to have a photon there, and the photon is not coupling to any of the gluons. Right, I mean, think about the gluon is not charged under the U1, obviously. So what is the result? Well, the result is that the amplitude should be 0. How do you see this in the structural constant basis? Structural constant involving the photon are 0. There's no such structural constant involving the photon. This is not clear in this representation, however. Yes. So if you consider, but you can choose, so you just say, well, my group is UN now, and I want to consider structural constants are the same, so you don't change the first representation of the amplitude. And yeah, I have if I take state 2 to be a photon, now needs to be 0. It is taking that to be a photon in the trace basis means that I just take the trace to be proportional to the identity. Right, so what do I get after doing this? I get traces in which there is not 2 because it's being replaced by the identity, and all the other are in a fixed ordering. So these are proportional to all partial amplitudes that have the same ordering for the other external states, and 2, since it has been replaced by the identity, comes in whichever position. So this is a cancellation between partial amplitude, which was obvious in one language and not so obvious in the other. The other language being the one where I have the traces. All the partial one are different. Well, it depends on the theory, but yes, the partial one would be different from 0. So these are not 0. Yes, indeed. And of course, I have different of these identities depending on which particular leg I am using, and some of them will be dependent from each other. So it's a little bit difficult just with this piece of information I have on the blackboard to understand what will be the dimensionality of the basis of partial amplitude. How many independent partial amplitude can you find? Yeah. Yeah. Yes, I mean, I see this actually, I think about this more as a relation between the kinematical part. So I think that because these are they just have kinematic information, right? And so this needs to be a relation which involves them, but also it can be seen as a consequence of what particular relation do the structural constant obey, in a sense. And there is one piece of information here which is quite important and was missing in the first organization of the amplitude I gave you, which unfortunately I have deleted here. So here there is, I mean, I gave you a recall, like go back in the notes, I do not know. This is, of course, written also in terms of structural constants, but that way of writing this relation with a structural constant was obviously not unique because structural constants obey Jacobi relations. So I just gave you something out of a Feynman diagrams, which was obtained with a particular choice of the reference momentum such that one of the diagrams was 0. What happens if I want to use the Jacobi relation? Actually, this is the next thing I wanted to mention. So let me just say that the Jacobi relation in this particular case with the F tildes is something of this form. And I am just considering, as usual, perhaps I'm keeping A fixed, and then I'm considering cyclic permutation of the other three, and then I am the result is equal to 0. This is something, this is the famous, I would say, Jacobi identity, dB, so C dB, C dB, same cyclic ordering, one term missing, A D, X, F tilde, X, B, C. So C dB, same ordering, this is equal to 0. Okay, so what does this mean for us? Well, actually, consider an amplitude at 10 points, and let's consider this in a graphical form, if you like. Something I will do a lot from now on is drawing different graphs. So I can represent this just by choosing the same ordering f. So a vertex here is associated to an f, a, b, x, and then x, c, d. So this will be something of this form. Of course, this is in a sense a graph not carrying information about which state you have. In some cases, you want to also convey that information, but there would be a minus sign, B, C, and how do you see that the minus sign? Well, there is A, C, X, okay, X, in this particular case, is B, D, not DB, so I need to put a minus sign. And there is also another minus sign, AD. And here the line is like this, BC. And this is equal to 0. Okay, so this relation can be used. And as a consequence of that, like, let's consider that I have a particular structure of an amplitude at 10 points. So let me just say, let me make a claim in this respect, a claim that operationally you can try out on your favorite endpoint amplitude, or at least color structure. So we pick leg, say your external state, if you like, 1 and n. And then through repeated use, the Jacobi, all trace structures can be brought to a particular form, which sometimes is called a multi-peripheral form, and is done as follows. We have the index corresponding to 1 and then displays like this, and then a permutation of the others, any permutation of the others, is inserted in this way. So let's say this would be a sigma of 2. This would be a sigma of 3, a sigma of n minus 1, where this is a permutation of those indices. Okay, very good. So, so keep in mind, so what is not one of these? What doesn't fit into this category, right? It would be something like this, for example, right? In which you have that the external states or the traces corresponding to an external particle are not inserted directly on this line, but instead there is a contraction with an internal index. And of course, all of this using, you see, I think, quite well from the graphical rules that I can use this relation to express this graph as a difference between the other two, thereby expressing this as a combination of multi-peripheral graphs. Yes, sorry. Yes, so this has to do on how the labels are associated to the structural constants. So the way I read the structural constant here is that I go in the same direction, I mean, my particular case clockwise around the point, and I have disordering, right? So here there is, let's look at this vertex, A, C, internal line, AC internal line, okay. But now there is internal line, so X, internal index, B, D, by the same ordering, right? Here I see DB, so I need to flip the sign. So it's just taking care. Same thing in here, you have ADX, this would be DAX, so there's a change of sign. And then there would be XBC, this is the same, so there is a change of sign here, and this is a -1. Yes, so in a sense, these signs are a little bit conventional in the way I associate graphs to structural constants. Ultimately, the structural constants are what I want to write down. The graph is a shorthand notation for keeping track of those. Very good. Any other questions about this? Does everybody buy the statement that through a repeated use of these rules, you can get to here? Yes. Yes, you would need to have a crossing graphs, but this is just what the permutation does. So you can say that the permutation graph, okay, in this particular case, this is, yeah, sorry. Let me just say, perhaps I can represent this, but I have a CP. Very good. Anything else? Practical questions, how to get from step 1 to step 2? You can see that if I draw, so here I have to pick, of course, two external lines. If I draw the external lines between the two in the horizontal, then I can have a certain number of internal lines which attach to this, right? And a repeated application of this, each time I apply this, I can reduce the number of lines, of vertical lines, if you like, in this representation until I go down to 1. And then it cannot be reduced. These two cannot be simplified. And it turns out that I have used all Jacobian relations after that. So there is a particular basis here. I mean, this has a name, and this is called the DDM basis after Del Duca, Dixon, Maltoni. Okay, so very good. So at this point, we then using this basis, or rather the statement of the basis is the following, that our amplitude, color dress, endpoint can be expressed as, well, coupling constant, which I think had probably not appeared explicit in some of the previous expressions. And then there is a sum over permutation here, and this is n minus 2. This permutation have n minus 2 elements, because now the first and last line are in a fixed position. This would be sigma of 2, sigma of n minus 1, and n would be in a fixed position. And now we don't find the traces yet, but we find these particular structures, A1, sigma of 2, and then there would be, say, an X, an internal lines, F, X, A, sigma let me be uniform in notation. This is A sigma of 2, believe it or not, A of sigma of 3, Y, and then there's a bunch of structure constant, and we end up having an F with one of the internal letters, and it ends with A of sigma n minus 1, A of n, fixed position. And these are normalized with my tilde. Okay, so this is the DDM representation or presentation. Very good. Okay, so I think that this is a good place to take a little break. What comes next is the relation between this and the partial amplitudes. Because so far, these A tildes are just whatever comes in front of this particular color structure. But we will see, or we will observe that these are indeed the partial amplitude, so the tilde will go away. Questions before we take a 15 minutes break? We can start again. Before I continue, is there any question about what I said just before the break? I realized that there's been many questions. There's been less questions than usual. So please let me know if you have questions. Okay, I see no question. Okay, so the last step remains to actually relate these amplitudes, which we have seen in the DDM representation, with the partial amplitudes. And this is done through an observation. So after a while of staring at the trace representation of this structure, which occur in the DDM basis, we get that their expression will be something of this form. So let's say that we have like 1 and 2 in here, and then we have f of say y, let's call it an minus 1 an. So you express this into a trace basis, and you are getting, of course, a trace in which the ordering is the same. You are going to get, of course, a term. So I should have another line here. A term in which the ordering is reversed. So you would have ordering of T an, T other T an minus 1, all the way to T a1. I mean, this is necessary by the reflection property also, and then many other terms. Now, the observation I want to make, which is an observation that you can, of course, make already at 4 points in the explicit presentation I gave before, is that the one displayed are the only 2 terms where TA1 and TAN are next to each other. Modulo ordering. So here the correct ordering would be A1 AN, and here would be AN A1. You can verify this with some simple examples if you like, and you see already in the presentation of the amplitude I provided. This actually tells us something quite important about about the interpretation of those terms. So namely, we identify this AN tilde amplitudes, the one in the DDM representation, with the partial amplitude. With same ordering. So in other words, we have found like this implies that there are, I should say, n minus 2 factorial independent partial amplitudes. Okay. So there are, I should say here, very important qualifying, at most, and minus 2 factorial independent partial amplitudes. Also, something that you may wonder is, say that I have a partial amplitudes obtained by having, which is not in the form in which one is first and then is last. Can I relate that to a partial amplitude, such as the ones which occur in this representation? And now, by the way, I am allowed to drop the tilde in here. Actually, this is a result I give without a proof or an argument for that, but these are known as the Kleist-Coif KK relations. And they can be stated in the following form. So let's say here we keep n fixed, and we have amplitudes in which one has different positions. And these are beta and alpha are two orderings of some subsets of the external states, which is not corresponding to 1 or n. Then we can express this to minus 1 to a number of elements of the set B, beta, as a summation over particular permutations of the remaining legs. Let me just use, for consistency notation, square brackets here. 1 sigma n. So this is an expression, of course, of partial amplitudes which are not in this set of n minus 2 factorial elements, and these are the ones which are in these elements. And here, this permutation, I mean, the physical content is in this permutation, are obtained by something which is called shuffle products. So the shuffle product is obtained by permutations in which the internal order of the elements of alpha and beta transposed is preserved. And I think the naming here really helps you understand how it works, because it's like you're shuffling two decks of cards. Each of them have an ordering, but how you do the shuffling is preserves that ordering, but there is freedom of like how many elements of alpha, say, come first, and then an element of beta transpose, and then some other elements of alpha, and so on and so forth. This is the number, and beta is the number of elements in beta. And these are known as the Kleist-Coif relation. So IJF relations. Okay, very good. And that question here should be very much in the forefront of your minds. Namely, is this all that there is, or are there other relations among partial amplitudes which have more complicated forms, perhaps? And actually, the answer to this question is yes. There are other relations, which are also called BCJ relations, which allow you to go to a basis which is not minus to n minus 2 factorial, is n minus 3 factorial. But they were not known until very recently, comparatively speaking. I mean, until 2008. So this has been one of the reasons for progress, recent progress in the field. And I will discuss those and provide some examples and discuss how they are related to color kinematics duality in the last lecture, or the second to last lecture, depending on how quickly I can move. Okay. Very good. Questions about this? Yes. Sorry. Mm-hmm. Okay. So how do we identify? Very good. So the way we identify this is by essentially looking at what kind of, I mean, expanding this in the trace basis, right? So we're going to have a trace basis here in which we have elements where you have the ordering of these two. And then we just consider, you know, what is the part of this expansion of the structure constant, which is proportional to a given number of traces here. And we note that there are only two terms in which A1 and AN are next to each other in all this particular in this particular expansion, right? So this is just this term will have, you know, these are the two terms in which A1 and AN are adjacent to each other. And then inside we see that this is the usual sigma, right? The ordering, which is the same as this sigma 2, sigma n, right? So this is the same as this is the same as what you get for a partial amplitude. So imagine that you are considering all these sums, right, with different sigmas, which is your amplitude. And then there is the 1 and the n, which are in first and last position, and with this color structure. Expand them in terms of traces. So what are you going to have? You're going to have terms in which the traces TA1 and TAN are next to each other, and there's a sigma. Then there's other trace terms in which 1 and n are not next to each other. We're not going to consider those. And then we're going to have, of course, you know, terms in which A1 and AN are next to each other, but the ordering is different. And now each terms of those traces is proportional to a partial amplitude. And you can see that if you have on the other side the expansion in terms of partial amplitudes, those terms match, right? Does this make sense for you? So that leads to the identification. Okay, that's a very good question. I realize probably I had not explained that super well. Other questions about this or follow-up questions about that? And here I am relying on, in a sense, this observation. So satisfy yourself with this observation. You can just be happy that I tell you. You can be happy at 4 points that you noticed that, or you can try it out, or you can attempt a proof of this. But this is the piece of information that is necessary for making that identification. Yes. Any other question? No, sorry. You go ahead. Students first. Why? So beta as opposed to alpha? Because I flipped the order. So the -1, I have flipped the order in here, in a sense. So you can say, I mean, one thing I would check about this formula, I mean, not one bother yourself, but just as a consistency check would be, okay, is this consistent with the reflection identity, right? So if you do a reflection identity, then you start having alpha playing the role of beta, right? And of course, you know, you say beta is not playing I mean, there is a difference between beta and alpha in here, at least implicitly, namely in the fact that here n is in fixed position, so I don't need to move n, and 1, I need to move it to the prescribed position. Of course, you can have an identical or similar set of identities, which is obtained by relabeling, in which perhaps you are considering amplitudes in which n has different positions, and you're trying to relate them to amplitudes which are in this form. In that particular case, beta and alpha would play complementary roles. But here there is an intrinsic difference between alpha and beta. There is the fact that beta gets flipped in terms of ordering. So this is how I understand this sign. And this is consistent with reflection identity, which, as you can check. I hope you are a little bit less bothered with that. Okay. You had a question before, sorry. Okay, that is very good. So partial amplitudes are supposed to be gauge invariant. Yeah. Yes-ish. Does an amplitude have an independent physical meaning? I mean, a cross-section, because different people will tell you, yes, yes. So they have as much of an independent physical meaning as the overall amplitude. Yes. And they are considered, I mean, they are gauge invariant. They are gauge invariant. Yes.
So if you give an amplitude, say I know how to build an observable pattern.
Yes.
So if you give a partial amplitude, it's not obvious to me. What should I do to get a complete observable to be tested in an experiment?
So you should, it depends really in what form the partial amplitude is provided, because I assume giving you one partial amplitude is almost the same as giving you all partial amplitudes if you're allowed to do permutations, because there's the dependence on the ordering which you have, that is. So for example, at 4 point, you could see right away that I was writing one of the partial amplitude and then permuting labels and get the other ones. So in that particular, yeah, yes, yes. In a sense, yes. Assuming that they are giving in a presentation where the labels are labels and I can permute them, then I just multiply them by a trace, use a sum over permutations, or rather use the relations which I have, I mean, somewhere here, and then this is gauge invariant. So this allows you to reconstruct the full amplitude. Yes.
How much of this is, let's say, easy derived from the string instruction for open strings on the boundary of the disk, let's say? You understand the cyclic symmetry and the fixed symmetry?
Mm-hmm.
Can you?
So,
I was going to raise that point before.
okay, so what?
There is one thing I know.
Yeah. Mm-hmm.
That first of all, you have more fewer independent in this case. Just take for point.
Mm-hmm. Yeah.
In that case, you have 3 dependent ones. Here you have 2, I think.
I mean, so in this particular case, yeah, I have 2 amplitudes, but I really have 1 amplitude.
That you're looking at particular excitation of the strings that could simplify, not because you're looking at massless modes.
That is a possibility.
Quite translate the fact that we put partial amplitude somehow in theory would be like a very trace.
Mm-hmm.
And here they have combination. Now at some point I thought it was because we were doing SUL.
Mm-hmm.
Now in theory you cannot do SUL. Because the amplitudes have, I mean, there are more independent amplitudes if you want.
Mm-hmm.
In that case you must do now if you do UN, there must be a bit of translation.
Yeah, there should be. I mean, so one can see, okay, BCJ relations are a consequence of string monodromy relations. So there is an understanding of that part. This should be easier to get, though. Like, yes. No, indeed. There should be a translation. I would have to think a little bit about that.
The independent amplitudes are more in that case.
Mm-hmm. Yeah. I'll think about that. That's yeah, indeed. Maybe we can give a result on that. Yeah. Okay. Any other questions? Your other question? No. Okay. Very good. All right. So now I would like to change topic a little bit, and having sort of given an idea of how, number one, to treat color, and number two, how to organize amplitudes and what independent pieces you have at higher points, I would like now to discuss some examples of tools that you can use for getting endpoint amplitudes in terms of lower point amplitudes, namely recursion, on-shell recursion, or sometimes it is called as BCFW recursion. So fundamental realization behind these methods is the fact that momenta are perhaps better treated as complex, in which case we can ask ourselves the question of what are their analytic properties. So on-shell recursion is, in a sense, a construction of our point amplitudes in terms of lower point amplitudes. And there is by now a general intuition, at least you should have, based, I mean, not necessarily on these lectures, but from previous knowledge about the importance of factorization properties for amplitude. So namely the fact that you have an amplitude at n points or even at 4 points, and you can see this really as it is manifest in a Feynman diagrammatics as a result of certain exchanges of physical particles, which you see as different exchanges. So there's different implementations of this basic idea, namely of reconstructing higher point amplitudes in terms of factorization properties from lower points. Here I would like to focus on BCFW recursion, which is due to Brito, Cacciazzo, Feng, and Witten in a paper, seminal paper in 2005. Okay, so the basic idea here is quite simple to explain, which is also why I think this is a very easy prototype sort of for recursive construction of amplitudes. So the basic idea is one parameter deformation of momentum. So even if we claim that momenta are complex, doing analysis of multiple complex variables can be complicated. So in many situations, what we want to consider is a one-parameter deformation with a complex parameter, and then we have a function of one complex variable. So namely, what I would like to do schematically is that my momenta, and more in general, also my polarization, so the kinematical data becomes a function of this complex variable. And then we have, of course, that the amplitude becomes a function of this complex variable, and we use this as a way to study the poles and hopefully reconstruct the amplitude when the complex parameters becomes equal to 0 based on the position of these poles. So in particular, we're going to have a deformation, and this is, of course, restricts the form which you can have over complex variables, and then a Q here, momentum. Don't confuse this with the reference momentum I use for the polarization. This can be the same, or it can be a different one, most likely a different one. Now, indeed, a first requirement which we can impose on this deformation is that I want to stay on shell. So p squared of the deformed And sometimes let me establish a little bit of notation. So quantities which are deformed, I put a hat just to remind myself that they've been deformed. So in this particular case, we want that the deformed momentum are still on shell, and we also want that the deformed momenta are still conserved. So they add up to 0. So we are still conserved and we stay on shell. And now the question becomes what is A on the complex plane as the function of that complex variable. Okay, so the first thing which we can do is that from these conditions, sorry, I should write it here, we can see right away that the sum of the QI needs to be equal to 0. This is to have conservation. And also, well, now we have to do a little bit of extra assumptions here, but let's assume that QIs are also null momenta. In this particular case, then we would have that PI dotted into QI needs to be equal to 0. And let me just say QI squared is equal to 0. So this actually is a direct consequence of this relation. Okay. So now this is the general framework of on-shell recursion. I don't think it's necessarily named BCFW. The BCFW is a very simple example of that, which uses spinnericity variables. So the next step is we pick 2 external states. We don't need to do so, but the simplest deformation will involve 2 external states. I cannot do that with a single one, otherwise I would have problems realizing this. So we pick 2 of them, and let's call this for simplicity different. I mean, the textbooks sometimes pick 1 and 2, sometimes 1 and then. I just pick the first and the last. And then I use the spinnericity variables. In this particular case, I have that Q1. I take Q1 to be due to momentum conservation minus Qn, and I write this in spinnericity variables as 1n. So essentially, I take the lambda spinner of the leg 1, and I take the lambda tilde spinner of leg n. And it's easy to verify that actually this solves the conditions, right? So I mean, it is manifestly written as a null momentum. So check, obviously solves momentum conservation, and then you consider both Q1 with a scalar product with the nth and the 1 momentum, and you see because of them coming with 1 spinner from one of the external states and the other from the other one, they give you a 0. So this is a perfectly good choice for our recursion, and this is equivalent to actually having a shift. Principle, this is a particular case of a more general framework there, but this equivalent, or this is a shift really, which happens already at the level of the spinor variable. So this is the same as essentially shifting the 1 square bracket by n, proportional to the complex parameter, and the angle bracket of the n by 1, with the other spinors unshifted. Okay, and I call this, in terms of nomenclature, just to remind myself what has been shifted, of which leg, and whether it's the angle or the square, I call this in this way. Okay. Very good. Questions about this setup? Before we start using Cauchy theorem, it's important that we're all familiar with this setup. Two things I want to emphasize is that it's immediate to check that these conditions are satisfied, which are required by interpretation of amplitudes, but it's also, you can see right away that some things are happening with these shifts. I mean, it's by no means unique. In fact, there will be an industry of different authors preferring one or the other shift. Nobody tells me it should be involving only two external states. I can have many external states if I like. There's a variety of shifts. Already these picks two particular external states which play a preferential role. It's one of the simplest, but it's not unique. And then there's many, many possibilities. So appreciate this. And by no means I'm telling you that this is the only way of doing recursion. I'm just giving you this as a simple and very historically important way of having an example of recursion. Okay, so the next step here would be to now look at the singularities of A as a function of the complex parameters. So on amplitudes, here we will use the fact what we know about amplitudes from Feynman diagrammatics. So amplitudes for us are not mystery objects. These are things which we know how to construct with Feynman diagrammatics. Just we don't want to use Feynman diagrams because they are cumbersome or complicated. And imagine here that you have a very complicated amplitude. Perhaps it's 100 external states. I don't know. So if A is obtained from Feynman diagrams, we know the position of the poles. The poles are there. There are poles for a certain value of the complex variable in which, poles when a propagator goes on shell. So in this particular case, we have that this will be encountered at a certain position. So perhaps it's useful to represent the amplitude in a certain way. We have a number of external states, and this is in a sense a channel representing a particular propagator going on shell. What is the momentum which is exchanged here? So let's consider here, I call capital I the set of external states which go into this blob. And then the total momentum here undeformed would be pi. And then there would be a piece here which depends on the deformation parameter. I use this as capital Q. If I have just two momenta which are being deformed, this can be plus or minus the Q which I have introduced over there, depending on whether it's Q1 and Q1. So this would be the momentum which is associated with this propagator, and then we have here two amplitudes, one on the left and one on the right. And here implicitly I'm going to have the shifted moment, so I have already decided that P1 will be shifted, so it's 1 here. There's a Pn here, which is also shifted, and the other quantities are P2, Pn minus 1, and they are like as in the normal amplitude without any shift. So in this particular case, I can actually study the behavior close to a pole because I know that this is the pole is produced by this propagator going on shell, and then this is the product of two amplitudes with a factor of I. And if you really want to keep track of numerical factor, then you have to think a little bit about what is the relation of say that we are considering for simplicity amplitudes involving gluons. Here, this propagator is not going to be just 1 over p squared, right? This is going to be something which is would be minus I eta mu nu, and then divided by the piece which generates the pole, the 1 over p squared. If you want to relate this with on-shell amplitudes, you would have to replace eta mu nu by a completeness relation in terms of external polarization. This is the relation I gave you yesterday, inviting you to prove it. And that the relation is a factor of, there's a factor of I coming from the numerator. So this is where the factor of I is coming from, if you want to be careful about that. So here we are going to have an amplitude on the left and on the right, having taken this leg to be on shell. This will be shifted, so they will be functions of the complex parameter, but they will become function of the complex parameters at the pole. And here, at the pole, we're going to have that this is this is the propagator coming from squaring these quantities, keeping into account, of course, that the Qi is designed to be a null momentum. Okay, very good. And of course, this will be close to a pole, which I indicate as Zi. And the value of Zi will be the one in which the denominator vanishes. So I can say right away that Zi is defined as minus pi squared divided by 2 Qi dotted into P. Okay, very good. So at this pole, when I'm evaluating the residue of this pole, I'm going to have that the amplitudes here, number one, they go on shell, so this intermediate channels goes on shell, and number two, they are evaluated at that one particular value of Zi. Okay. Now what remains to use, and then I should say for notationally, let me write that Pi here is defined as the sum of all the states which enter in my particular set of states which are on this side of the amplitudes, and that is the total momentum that they have. There will be, of course, there will be several of such poles depending on different propagator which can go on shell in your diagram. And which propagator can go on shell depends also partly on whether you are considering color-ordered partial amplitudes or just full amplitudes, in which case you would have more combinations. If you have just ordered partial amplitudes, you can have combinations here in which I and the complement maintain that order, right? So I can actually have less options in that particular case. At this point, of course, what I want to have is the amplitude. My original amplitude is A of 0, right? So I can use Cauchy theorem. And I express the amplitude I want, A of 0, as the integral on a circle around the complex parameter being equal to 0 of A of Z divided by Z. And then, deforming this, I express this as a series of summation of all, and this is a very shorthand notation to say depends on all possible sets I such that a propagator can go on shell, and then it's going to be a sum of the residues at the complex parameter having the Zi value, and here I have this particular combination, which also, of course, has a 1 over Z value. And there's a loophole in here, right? There's a very big assumption, which is, I mean, I wouldn't say the drawback of this method, but this is something that you have to be very careful about, and that in some cases is discussed very quickly, or even put under the carpet here, the fact that you can have, of course, a pole at infinity. Okay, and I would like to talk starting next time, or I will provide an introduction now, depending on how many questions you have, about the poles at infinity. Let me just, to finish this, and then I would assume you have some questions, let me just express the residues using the expression I have above. I use just what I wrote over there, and I write this as minus I AL at the particular value of the residues, AR. So these are, just to emphasize this, these are not undeformed amplitude. These amplitudes are deformed by the complex parameter taking the particular value of the residues. And then here, if you go through some simple algebra, you have pi squared. So the final expression, which is the core formula of the BCFW recursion, is that you sum over all possible factorizations of intermediate channels the product of two lower point amplitudes. Hence, you are constructing difficult amplitude from simpler amplitudes, evaluated at this shift. So it's not really amplitude, these are shifted amplitude, dividing by pi squared, where this doesn't have a hat. Okay, so the pi squared is the unshifted one. Otherwise, it would be a zero. So don't make the mistake. Plus a pole from infinity, and this or a term from infinity, and you have to ask the question which factorization channels are allowed, depending on order or not order, and you have to have the questions. What is the behavior at infinity? So in other words, we are almost done in the sense that we have a very nice suggestive formula for recursion, and this is an implementation really of the bootstrapping philosophy, right? Building amplitudes from, well, not from nothing at this point, but say 4 points from 3 points, 5 points for 4 points, and so on and so forth. But there is a caveat here about the pole at infinity, which we have to discuss. Questions about this? Yes. Yes, so when I'm taking the residue, okay, so when I'm taking the residue, I write this as z minus zi, multiplying this product, of course. But then always keep in mind that there is also a piece coming from this, right? So this evaluated as zi, as you use that formula, and indeed it cancels the q dot into the p, and you're left only with this. Does this make sense? Just basic algebra, in a sense. Do I need to provide more details? Okay, sorry. I'll take the absence of an answer to a yes, for a yes. So this would be, I can write this as 2 qi dotted into pi, z minus zi. Yes, just using this expression for zi. Yes. Then I evaluate the residue. So this also, I mean, this is part of the residue, the coefficient of z. This is the standard form of normalization 1 of the pole. This needs to be multiplied by the 1 over z. I mean, you have an extra factor in the evaluation of the residue. All right, let me try to find some room. All right. Okay. So, so the evaluation of the residue becomes, we have the residues of A divided by Z. So the evaluation of the residue becomes AL, AR. But here we have, ZI. Okay, and we have the overall factor which we have collected, which is this 2 qi dot into pi. But this factor, I mean, using the definition of Zi, which we have here, indeed, you just get a minus sign, pi squared. The pi squared is precisely what is left and what enters the final formula. And the minus sign, of course, cancel the minus sign in here in the residue formula. Okay. Other questions about this? Okay, so I don't feel like starting a new topic or either the study of B infinity in, I have 2 minutes left, so I think that this is a good moment to stop. Oh, yes, sure.
A short answer, I guess you
Yeah.
talk to that.
Yeah.
About this residue at infinity.
Yeah.
I mean, there's a physical meaning, or it is a technical, crucial debate. Sorry if the question is naive.
No, it's not naive at all. I do not really know. So my inclination would be to say that we are learning something about hard scattering here. So in the sense that what is the behavior of Z going to infinity? This is a situation in which, well, the two external states that I have picked have very high momentum, right? Although in a complex direction. So there is a bit of I mean, I'm not sure it's physical in that respect, but I think that there is some information there about scattering for very high momenta. And the way we're going to discuss this, and the arguments which are usually invoked for arguing that the behavior at infinity is good enough. I mean, ultimately, our goal will be to show that for theories we like and for certain shifts, the behavior of the amplitude at infinity goes like 1 over z, or 1 of z squared. And we'll do this using some sort of background field method, simplified version of background field method in which we argue that we sort of consider the one particular line as a hard line, the one from 1 to n, and then we have sort of a bunch of soft gluons, you know, inserted on that. And then we'll try to argue that, look, the behavior of the amplitude, the leading behavior of the amplitude is something like 1 over z. This has a simplified, this is a simpler calculation than actually calculating the Feynman diagrams, in the sense that you just care about the leading z behavior, and that you just have these two lines which have a large momentum. But I think there is some physics there, but it's a little bit, confused by the fact that we are considering hard momenta, but in a complex direction. So I don't have a direct physical intuition, but I think there is physics, yes.
Sorry, I would have just expected the B infinity to impose the interactive part of the app.
Really?
Otherwise, it just seems like Wick's theorem and in a powerful form seems too good to be true. The theory is reconstructible from lower correlations.
Well, I mean, it is, well, it depends what you mean from lower correlations, because you have fundamental information about a theory which goes into 3-point functions, for example. So the question is, for example, think about the level of Lagrangian, right? If I give you the cubic part of Yang-Mills theory, can you reconstruct the quartic part? The cubic part of Yang-Mills theory, right? Just up to 3 vector fields. Can you reconstruct the one with 4 vector fields? The answer is yes, right? You just know how to do gauge invariance, and the gauge invariance essentially fixes that. So that, you know, you have a covariant derivative, you have an f mu nu, and eventually, for Yang-Mills, the f mu nu, it is something which involves a piece with 1 field and then a piece with 2 fields, and the only way you can do consistently, you reconstruct it. So there are 2 ways of looking about this. The physics can be at 3 points, or at 4 points, or it can be like that I cannot use this tool because it would be too good to be true. And it depends actually on the theory. I mean, an example of a theory which is not constructible is a theory which doesn't have 3-point amplitudes but has 4-point amplitudes, right? I mean, if you start having phi to the 4th theory, for example, well, you're not going to be able to construct it in this way. So that's an example of what you were saying. This is too good to be true. But my favorite example would be Yang-Mills and perhaps gravity. And I would say, well, at 3 points, I am confident that the theory specifies, and that this takes into account all the corrections consistently. Yes, it is very heavily theory dependent. Precisely. Unfortunately, not only theory dependent, it's also shift dependent. So I choose one and then, and which polarizations, this will be dependent. In fact, you'll see tomorrow some examples of shifts which are good and shifts which are bad. So yeah, I think that this is, I wouldn't say the limitation. I mean, it would really be too good to be true, right? If this works for all theories and I don't have to check anything and all shifts work, right? So there will be some knowledge there about what shift work and what shift doesn't work, but I hope you can appreciate that once I show, or once I will show that a shift works, it works for 5 points, 6, 7, it keeps working. So there is, this is a very powerful technique once you have an understanding of what works in terms of shifts. And also can be a treacherous technique if you end up having the wrong shift. Okay. Anything else? Otherwise, I think we are all very hungry and we should go to lunch.